Good morning, everyone. My name is Ronaldin Yujie, and today I will present my experiment entitled Determination of the Acceleration Due to the Gravity using the Simple Pendulum Oscillation Method. The purpose of this experiment was to determine the value of gravitational acceleration g using a simple pendulum. We also investigate how the length of the pendulum affect the oscillation period and whether changing the mass of the pendulum board affect the result. A simple pendulum consists of a board suspended by a light string. When displaced by a small angle and released, it undergoes simple harmonic motion. The period of oscillation is given by the equation T over 2 pi square root L over G. From this equation, we know that the period depends only on the pendulum length and gravitational acceleration. It does not depend on the mass of the pendulum board. By squaring the equation, we obtain a linear relationship between T squared and L, which allows us to calculate G from the gradient of the graph. In this experiment, we used two pendulum boards with mass of 31.3 grams and 58 grams. The pendulum was released from a constant angle of 5 degrees to satisfy the small angle approximation. The pendulum length was varied from 20 cm to 80 cm. For each length, the time taken for 10 complete oscillations was measured twice using a stopwatch. The average time was calculated, followed by the period T and T squared. Finally, graphs of T squared against L were plotted manually and digitally using the geometrical sketchpad. The gradient obtained from each graph was then used to calculate the acceleration due to gravity. Our result shows that as the pendulum length increased, the time taken for 10 complete oscillation and the oscillation period also increased. The graph of T squared against L produced an almost straight line, which agrees with the theoretical equation. For the 31.3 gram pendulum, the average value of G was approximately 9.77 meter per second square using the hand plot graph and 9.78 meter per second square using the digital graph. For the 58 gram of pendulum, the value were approximately 9.74 meter per second square for the hand plot graph and 9.81 meter per second square for the digital graph. All these values are very close to the accepted value of 9.81 meter per second square. Our experiment successfully confirmed the theoretical relationship between the pendulum length and oscillation period. According to the pendulum equation, T squared is directly proportional to the pendulum length. This means that when the pendulum becomes longer, it takes more time to complete one oscillation. Our graphs show a strong linear relationship, indicating that the pendulum follows simple harmonic motion under the experimental condition. Secondly, we compare two different pendulum mass, which is 31.3 grams and 58 grams. Although the heavier pendulum experiences a larger gravitational force, it also has a greater inertia. These two effects cancel each other out mathematically. Therefore, the oscillation period depends only on the pendulum length and gravitational acceleration, not on the mass. This is supported by our experimental result because both mass produce value of G that were very similar and close to the accepted value. Another important finding is the comparison between the hand plot graph and the digital graph. The digital graph produce more consistent value. This is because the software calculates the best fit line mathematically using all the data points, reducing the human error. On the other hand, the hand plot graph depends on how accurately we draw the best fit line and select the gradient, so small differences are expected. Although our results were accurate, there were still small experimental errors. The biggest source of error was human reaction time when using the stopwatch. Even a delay of a fraction of a second when starting or stopping the timer can affect the calculated period. Another source of error is measuring the pendulum length. The length should be measured from the point of the suspension to the center of the pendulum board. If this measurement is inaccurate, the calculated value of G will also be affected. Other factors include air resistance, friction at the pivot, and slight movement of the support, which can reduce the accuracy because they cause energy loss during the oscillation. To improve this experiment, we could replace the stopwatch with a photogate sensor or motion detector to eliminate human reaction time. We could also measure more oscillation, for example, 20 or 30 oscillation instead of only 10. This will reduce the percentage uncertainty. Finally, repeating the experiment more times and maintaining a constant release angle will improve the reliability and accuracy of the result. In conclusion, the experiment successfully achieved its objective. Thank you for your attention. I am happy to answer any question.